Now you will hear about formalizing polychromatic colorings of integers from Bhavik Mehta, Imperial College, London. That's a QR code for my slide if you would like them. That QR code will also be available in the corner if you don't have time to grab it now. Okay, thank you very much, and thank you for having me, and thank you for letting me speak again this week. I want to talk about a project I have been working on recently, which is related to polychromatic colorings of integers. The reason I quite like this project is that it involves a bunch of different ways in which one can use Lean. And so I'm going to hope to explore this idea and show you how Lean's philosophy and mathlib makes this kind of combined mathematics quite interesting and quite accessible. But first, let me tell you about what polychromatic colorings actually are. Then I'll talk about the formalization aspect of this and also about the computation aspect of this project. So we're going to start off with an arbitrary abelian group. If you don't like this, just think about the integers. In our cases, it will mostly be the integers, the reals, or the integers mod q. But most of what I'm going to say, at least in the introduction section, will work for an arbitrary abelian group. Here's going to be our key definition. Given a finite subset of our group, a coloring X of the group will be called polychromatic for the set if every translate of the set meets every color. So I'm going to take a group, say the integers, and color in each of its elements. So maybe 1 is green, and 2 is red, and 5 is yellow, or something like this. And I have a finite subset S, which is maybe -1 and 3. And I'm going to look at all of the translates of this set. And I want that in every translate, every color is represented. So in every translate, I see every color. Okay, so that's our key definition. Finitely many colors, exactly. So you must, because of this, you must have finite many colors indeed. Yes, thank you. So from this, we can define the polychromatic number, which is the largest number of colors possible in a polychromatic coloring for S, and this must be a finite number. And in particular, we can do a bit better than that. The number of colors must actually be bounded above by the size of the set, essentially the same argument you had in mind. And we could also say this polychromatic number is bounded below, because if I color everything in one color, then clearly in every translate of a non-empty set, every color is represented. Is this clear to everyone? This is going to be the key definition for the rest of what we're going to talk about. It's a fairly straightforward definition, but it might take a little bit of time to get used to. And so because of that, let's look at some examples. The first example I will give you is the set 0, 1 in the integers. And I claim this has polychromatic number 2. Well, what's the coloring we're going to use? We can just use the alternating coloring. Let's say red, blue, red, blue, red, blue, red, blue, and so on, in both directions. Now, every translate of my set 0, 1 is going to have one red element and one blue element. So this coloring is polychromatic for this set. And I can't use 3 colors, because with 3 colors, then any translate won't be able to meet any color. For example, the set itself, I don't even need to translate it, just 0, 1. That can't use all 3 colors. So there is a polychromatic coloring with 2 colors, but there is not with 3 colors. So the polychromatic number of the set is 2. And this generalizes. In fact, if S is any set of size 2 in the integers, then its polychromatic number will be 2. In fact, the last thing I quoted there works for any torsion-free group. And it's a fun exercise if you like to think about why it doesn't work if you have some torsion. But I won't talk about that case too much. But what happens if the size of the set is 3? It turns out then, oh, that's a typo, then the polychromatic number of the set may be 2 or 3. Let's see why. If our set is 0, 1, 2, then we can find a nice and easy 3 coloring. So I've drawn it here. I've even given you different shapes just to make it a little more visually interesting. We're going to take the periodic coloring, which is, in this case, gray, blue, red, and just repeat that. And that's going to be polychromatic for the set for the same reason as the early ones we saw. You take any translation of 0, 1, 2, and it has to use all three colors. But now let's look at another set. Let's think about 0, 1, 3 this time. This is a set of size 3, but no polychromatic 3 coloring can exist. This is not so clear, so let me give you a proof. Suppose we do have a polychromatic 3 coloring. Then let me think about the original set, 0, 1, 3. And this must meet every color. So without loss of generality, let me say 0 is the one which uses red, 1 is the one which uses gray, and 3 is the one which uses blue. It could be in some order, but I need to have all three colors for these elements. Now what we're going to think about is what color is 2? Because we're coloring the group, so and we're 3 coloring the integers. So 2 must have a color, and it must be red, green, red, gray, or blue. What happens if 2 is colored in gray? Well, then I have a contradiction, because I have this translate of 0, 1, 3 by translating up by 1. And this translation, which will be 1, 2, 4, that's used gray twice, which means it can't use both red and blue as well. Similarly, if it's blue, you get a contradiction by shifting up again. And if it's red, you get another contradiction by shifting down. So for this particular set, there does not exist a polychromatic 3 coloring of the integers. So given a set of size 3, the polychromatic number could be 2, or it could be 3. Let's think about this notion of having a polychromatic coloring with a given number of colors. It has some quite nice monotonicity properties. In particular, if I use fewer colors, then it makes it easier to find the coloring I need. If I use fewer colors, then all of my translates, they have less properties to satisfy, so it can't get harder to find the thing I'm looking for. So using fewer colors makes the problem easier. And conversely, using bigger sets makes the problem easier. If my sets are bigger, then I have more space to use the colors I need, and so the problem cannot get harder if I make my set larger. What this means is that if I fix the set, there's always some small number of colors which gives me a polychromatic coloring. In fact, one. One color will always give me a polychromatic coloring, and in non-trivial cases, 2 as well. And one might hope that there is some nice bound we can give in this case. What if I do the opposite? What if I fix the number of colors? I want to fix a number of colors. Let me say I want to use 5 colors. Will it be the case that if I guarantee my set is size at least 10, is there always a coloring I can find using 5 colors? Maybe 20, maybe 30. So is there some bound on the set size of the set I can give which guarantees that there is always a 5 coloring which is polychromatic? This is not so clear. This is not nearly as clear as the second bullet point here. But let's give it a concrete example. With 2 colors, sets of size 2 can always have a polychromatic coloring. I mentioned this in the earlier example. But this is not true for size 3. With 2 colors, a set of size 3 may not have a polychromatic coloring. So in this case, the small number of colors which works is 2. For 2. The size which works is 2, but it is not 3. And this question is sufficiently non-trivial that Strauss asked it as a conjecture. And to be very specific about what the conjecture is, if we fix a number of colors k, is there a large enough size m such that every finite set S, which is large enough in terms of m, has a polychromatic k coloring? In other words, such that every S, which is big enough, has this polychromatic number being as big as I wanted it to be. Okay, so that's our first question. Sorry? Oh, sorry. Yeah. This one is tricky. Okay. So I'm going to fix a number of colors. Let's imagine I want to use 5 colors. Is there a large enough size of the set that I could pick which guarantees that any set bigger than that size has a coloring with that many colors? So let's say I want to use 5 colors. Is it true that if I use m as 10, any set which has at least 10 elements has a polychromatic coloring with 5 colors? And like we say, this is easier if my sets are bigger. So one might hope that if m is large enough, we can find the thing we need. But that's not completely clear. It's not trivial to see why that's the case. But if k is 2, then we have seen that you can always find the thing. I'll keep this open for a few more seconds because this also took me some time when I first saw it. Everybody happy with this definition, with this question? Excellent. Yes. Yep. Yes. Exactly. Exactly. Every color must be represented at least once. I don't need it to be unique. So it's exactly. Exactly. So yeah, that's why I say using bigger sets makes everything easier for you. So now that we've asked this question, it turns out that the answer is yes. You can always find a big enough M which works. And in fact, the M doesn't need to be that big. The bound which was shown in 1975 was approximately 3k log k. So if I want to use 5 colors, then let's say roughly 15 times log 5, approximately. If you're bigger than that, then you can get the thing you need. I'm not going to be able to work that number out in my head, but it's some concrete finite number which will work. And you can kind of flip this around and give a bound on the polychromatic number, but that's not so important for now. Okay, so that's kind of the asymptotic case. That's what happens for large sets and large number of colors. But we can also make this much more concrete and much smaller. Let's just say I have a set of integers which has size 4. It's got 4 integers I've picked out. What's the polychromatic number of this set? This was an open question for a while, until it was resolved by these 7 authors in 2021, where they proved that if you have a set of size 4, there is a polychromatic coloring by 3 colors. Some of the sets will also have 4 colors, but all of the sets will have a coloring with 3 colors. And what I want to talk about to you today is the work in progress formalization of these 2 results. And in particular, the first one is finished. The second one, the hard part is finished and the easy part is not finished. So that's kind of the current progress. And there's this link, which I'll show again later, where you can see the code and all these things. Okay, great. So now let's move on to the formalization. Do we have any questions at this point? Yes. That's a great question. So for this proof, this is just for the integers. This one's just for the integers. For this earlier version, I think Strauss asked the question for the reals. I think they proved it for the reals. That means it also works for the integers. And it's fairly clear that their proof will also work for the integers mod k. It turns out, as we'll later see, this is true for any abelian group. It's not particularly hard to see, but I hadn't seen that statement written down in the literature anywhere before. But this is true for any abelian group. And in particular, the little o, kind of all of the implicit constants hidden in here, they all don't depend on the group. That's a good question. I don't know the answer off the top of my head, but yeah, this is a good question. I don't know off the top of my head. This is the one which has been studied since a couple of decades. I don't know of research in the other direction. Yeah, that's all I have for you. Okay, let's move on to the formalization. Here are some definitions. The first one will be our definition of what it means for a coloring to be polychromatic for a set. Hopefully, we've all seen enough lean statements by now, especially if you're paying attention to my talk on Tuesday, that this first definition tracks with what you expect it to be. We've said for every n, which is an element of our group, which is the thing we're going to translate by, and every k, which is a color, which is the color we're going to be looking for, there is some element in our set such that the translation of that element has the right color we need. So this is essentially just a direct translation of the original statement I gave you, that every translate uses every color. One of the things which is very useful when you're writing lean is to make sure your definitions make sense. And there are a couple of ways to do this, but one of the easiest, and kind of one of the first sanity checks, which is always worth doing, is proving very simple lemmas about your definitions. So I've given you 2 examples here. The first one is that if you have a polychromatic coloring, your set must be non-empty. Why is that? Well, 0 is always in my group, so let me translate by 0. And let me see what color 0 has. that must have some color. And so some translate must represent that. And so there must be some element in my set. And the second one is similarly trivial, and kind of what Filippo mentioned earlier, which is that if you have a polychromatic coloring, your coloring set must be finite. So here are our first two lemmas about the definition, so we can make sure this thing makes sense. And then from here, we can play the same game with the property of having a polychromatic coloring. So again, we have a definition and a simple lemma. And again, the definition follows exactly what you expect it to be. So the things I want you to take away from this is that the definitions for this setup are very simple. And we can also very easily prove the simple things we would like to do about this definition. But now I would like to find these colorings. I want to formalize this proof of Strauss's conjecture, which means I have some sets, and I want to find a polychromatic coloring of the integers for that set. And there is this generally useful principle in probabilistic combinatorics that if I would like to find something and it's not completely clear how to construct it, let's just try and make it randomly. So I'm going to think about all of my integers, and I have some number of colors I would like to use. I'm just going to, for each integer, pick the color randomly. Just toss a three-sided coin or whatever you'd like for each one, and pick your colors each randomly. Sometimes this works, sometimes this trivially works. In this case, it's not completely trivial that it works, but there is this lemma called the local lemma. And let me try to motivate why this is interesting. So Erdős and Lovas's proof of Strauss's conjecture introduced this lemma, which is sometimes called the Lovász local lemma for fairly obvious reasons. But what is it really saying? Let's step back a second, and let me think about, I have a collection of events. I've got a collection of events AI, and these are bad events. I just realized there's a fun pun I could make in there about AI being a bad event. But let's ignore that for now. I have an independent collection of bad events. Maybe they're different companies, who knows? And let's say each event has some probability less than 1 of succeeding, like the companies. If they're independent, then the probability that all of them failing is non-zero. There's just a fairly straightforward independence calculation. I would like to apply that to my context, but it turns out that Erdős and Lovász realized that the events they wanted to apply this to were not quite independent. What if they're not independent? This argument doesn't really apply. But instead, they kind of weaken this and showed that if the probability of each of them failing is, we can still show that the probability that they all fail is not 0, provided that each individual one is sufficiently unlikely and they are mostly independent. In a way, I'm not going to make completely precise, but it is something which can be made precise, and it's like, these are not too related to each other. So it's a weakening of the statement I wrote on the third bullet point, which is kind of more approximate and more useful in practice. Here's the statement. That's the full statement. I'm not going to go through all the details. But again, what I want to show you is this looks fairly similar to the statement in informal mathematics. So I have a probability measure. I have a collection of measurable sets which will correspond to my events, and I've bounded the probability of each one. Then, under certain conditions, I can say that the probability that none of them occur, none of them meaning the intersection of the complements of all of them. So the complement of all of them is that individual one doesn't occur, and intersect them all, that's all of them don't occur now. That probability is positive. And so this is a lemma which I proved, and that's very useful for this context. One tricky thing about, oh yeah, Michael. HPD. This condition, HPD, says that P is not too big relative to the other constraints. Okay, so this lemma has multiple different variants. The one I've given you here is called the symmetric local lemma. There is also a non-symmetric local lemma. There is also something called the lopsided local lemma. There are many different variants of these things. Some of them depend on how you quantify what mostly independent means. Some depend on how bounded you can make each one. In this case, I've bounded each event by a uniform probability P. Maybe you can't do that in context. So there are multiple different variants of this. And so one thing which goes into formalization in this kind of context is thinking about what's the right version to prove. And in this case, it turns out that there is one most general version, and you can use that to deduce the others. But the most general version isn't the one which is presented first. The one which is presented first is the one I presented to you, where I kind of motivate this by talking about independence and then weakening independence, and then you write down a statement like this. But this is not the most general one. It can actually be generalized, and I won't show you that because it's a bit more gnarly. But one of the things which goes into formalization is thinking about the right generality to state your theorem, which makes it easier to get all of the variants you need. While pedagogically, you might want to present the simplest one first, when formalizing, you often want to formalize the most difficult one first and deduce the other ones from it. And this is kind of a case where that showed up in practice. Okay, so this is very nice. How are we going to apply this? Let's make this a bit more concrete in our specific coloring situation. We're going to say our bad events AI will be a particular translation, S plus I, not receiving one of the colors. So the event indexed by I will be that one particular translation doesn't receive some of the color, or at least one of the colors. So this is going to be a bad event, and what we're going to hope is that with non-zero probability, it's possible for none of these bad events to occur, and if that's the case, then we find the thing we need. And like I said, these events are not independent because we're picking each color independently. And so if the two translations have some overlap, these are not independent events AI. But they don't overlap too much. It's kind of bounded quadratically in the size of the set. And so you can control the dependence reasonably well. And we can also estimate the probability of each event happening well enough. So it turns out this works in practice, but it has one key problem. The number of events in the local lemma, the number of events I have has to be finite. So I've got this thing fin type here, which corresponds to the number of events I'm looking at. It needs to be a finite collection of events. But in our case, we're taking all translations of our sets. And in the integers, that's infinitely many. So this lemma I've just described to you, it's a very nice lemma, but it doesn't actually work in our particular case. So one thing you might want to do is, maybe we can find a better lemma. But it turns out this is also a well-studied problem in combinatorics. But while we stepped out of combinatorics into the world of probability to get started, we're now going to step back to combinatorics and take another step in the direction of topology. So we're going to start by making progress with probability. Now we're going to come back and move into topology. So our theorem only works if you care about finitely many translations, which is good if you care about finitely many translations or if you have a finite group. But I want something like the integers or the reals, and these are certainly not finite groups. So I'm going to step into the world of topology and find a different solution. Now, there is this general argument in combinatorics called a compactness argument. And this is usually done ad hoc. It's more of a proof principle than it is an actual concrete method or a concrete idea. It's kind of a vibes-based thing. We use a compactness argument to get what we're looking for. And this is very nice conceptually. You think about compactness in some convenient way. But this is not particularly nice for formalization. Because I'm formalizing, I would like to have a lemma which I can apply in many different situations to recover this general argument about compactness. And so I went searching for what is the most general lemma I can think of which quantifies what this kind of argument is doing, that makes more precise what a compactness argument is. And through a bit of digging, I discovered this paper by Rado, and he wrote down a selection lemma. This was maybe in the 50s, and this paper has very few citations. Rado did a lot of great work, but this particular paper seems fairly unknown. But he proved this selection lemma. Here is the statement of selection lemma. I'll go through it in a second. But one thing I should say about this is that if you have proved this lemma, proving the de Bruijn-Urdrich theorem, which was mentioned in the earlier talk, that's a two-line proof from this lemma. So this de Bruijn-Urdrich theorem, which is a fairly well-known and fairly famous theorem, it's now in this live benchmark. That's 2 lines from this thing. And de Bruijn-Urdrich is usually proved using a compactness argument. So this one does correctly capture that aspect of the compactness proof. And it will do the same for us here. What is this thing actually saying? Okay, so I have alpha and beta, which are 2 types. I can just think of these as sets. And the thing I would like to find is a function from alpha to beta. Beta is finite, so I'm going to think of beta as my coloring set. Beta is going to be my source of colors. And I have finite many colors, so this makes sense and something to do. And chi is picked specifically to invoke the imagery of coloring. It's chi, it's a coloring just like before. And so alpha to beta is also a coloring. Yes. I'll come on to G in a second. Actually, yeah. So we're going to eventually construct a coloring of alpha, which is from alpha to beta. So a function from alpha to beta with some property. And it's going to be constructed in some way out of G. So what is G? G says for every finite subset of alpha, I will give you a coloring of alpha. So for every finite subset, for every patch of alpha, I'm just going to provide to you a coloring of all of alpha. And intuitively, we're going to think of only coloring that patch, but in the formalization, it turns out to be more convenient. For every patch of alpha, we're going to give a coloring of alpha. And the idea of this lemma is I'm going to take all of these colorings and stitch them together into one global coloring, which is called chi. So this is a kind of local to global type principle where I have lots of local colorings and I stitch them together into one chi. And in what sense do I mean stitched together? It's that for any other finite subset of the space I'm looking for, there is some extension of that so that the coloring I've constructed, chi, matches one of the provided things G. And just to be clear, that's G gives, for every finite patch, a coloring of the thing. Okay, so intuitively what's going on here, I've given you a bunch of colorings, and I've stitched them together into one big coloring, which is kind of constructed out of the smaller ones. And maybe it's becoming clear why this is going to be useful. Because in the earlier application we had from probability, for any finite collection of translations, I could find the coloring I need. But what this lets me do is if I've colored something for some finite collections, then I can stitch them all together into the big coloring I want. So I'm going to stitch the probability argument and this topological argument together to get the statement I'm looking for. But let's first talk about, yeah. Excellent question. Here's why it's a topological argument. It's in particular a compactness proof. And what we're going to do is use Tikhonov's theorem, that the product of compact sets is compact. And in particular, this is why I will use that. Okay. So we have this alpha to beta. I'm going to think of each beta. I will give it the discrete topological space structure, which is in particular compact because beta is finite. And then alpha to beta will be the product of alpha many compact topological spaces. So alpha to beta is itself a compact topological space by Tikhonov's theorem. And then essentially, I won't sketch the full details, but the thing we're looking for can be expressed as the intersection of many closed sets. And by by standard theorems in topology, if you have the intersection of closed sets in a compact space, that intersection is not empty, provided you have some finiteness condition, which is essentially guaranteed by the setup of this question. So the reason I describe this as a topological thing or a compactness thing is that its proof uses not completely trivial topological arguments together. Yes. Because at this point, I don't have any topological information about beta. And in particular, in applications, it's not useful in the broader context to think about beta as a topological space. It's just some finite set of colorings. So I agree this would go through if I said that beta is a compact space. But the idea of this lemma is to translate from the topology world into the combinatorics world. And so kind of it's nice for this lemma to be my abstraction boundary between topology and combinatorics. So it's useful in practice and kind of intuitively to think of this lemma as a combinatorial statement with a topological proof rather than topological statements. And like I say, this compactness principle appears all the time in combinatorics. So isolating into this Rado selection lemma helps formal reuse. I'm not convinced this works for every application of compactness in combinatorics, but it works for almost all that I've seen. So I think it's a pretty good way of thinking about compactness arguments in combinatorics and kind of, like I say, this is a good abstraction boundary between the two. Okay, great. So putting these pieces together, we can say that under some condition, this is a fairly mucky looking condition, but it is just a real number condition, based on the size of my set and based on the number of colors I would like to use, I can find the polychromatic coloring I need. So this has come from the two earlier statements. Almost directly, we just get out that under certain conditions, we can find the polychromatic coloring we're looking for. But this coloring is a bit messy, so let's make it look nicer. But first, it's worth noting that this bound doesn't depend on the group. So earlier, I could have hid some stuff in some little o's. But at this point, G has no assumptions on it other than being an abelian group. I haven't said G is finite. I haven't said G is countable, uncountable, has any torsion properties. It's just an arbitrary abelian group. And under these conditions, we can show that some polychromatic coloring exists, provided the numbers match up in a good way. But what does this good way actually mean? One way you can satisfy this condition is if M is at least 3k squared. That's fairly concrete. That's fairly direct. It turns out asymptotically this is not the best you can do. For this particular bound, you can show roughly 3k log k, which is the bound I gave you earlier. So this is the way Erdős and Lovász's proof of this claim worked. They went through these kind of steps to get there. And this is a mucky-looking bound. I've got a 2 log k and a 5.2. It doesn't need to be that. Something around that would probably work, and so that's why we just hide it into the little o of 1. And proving this last part is some calculus. It's some kind of analysis stuff, which is tedious but not particularly difficult. And so putting all of these things together, we can say that for sufficiently large k, in the interest of time, I won't explain why this means sufficiently large, but for now, just trust me, this means for sufficiently large k, for any finite subset of the group, if this set is large enough, which roughly means it's more than 3k log k, then there is the polychromatic coloring we were looking for. Okay, so now we've kind of fit all of those pieces together in order to prove this conjecture of Strauss following Erdős and Lovász's proof. And to do so, we've kind of combined a whole bunch of different areas of mathlib, used them, dipped into them, come back home for a while in order to get the statement that we're looking for. Okay, so we've used some probability, we've used some topology, we've used some calculus, and it's been really important in this process that all of these things work together nicely in mathlib. These are all kind of coherent in mathlib. Mathlib is this one very nice library which contains all of these theories in a way which is intercompatible. And that's kind of really important for this process to go through, because if they didn't play nicely with each other, I wouldn't be able to dip into one world and come back as freely as I can in this context. And the formalization of this, as we've seen, involves understanding the proof, sometimes restructuring the proof, sometimes generalizing, sometimes abstracting, and sometimes looking for alternative ways, and sometimes it's just translating. So it can involve all these different things in the process of going from formalization, so from informal to formal versions. You often end up with more steps in the formal proofs than the informal proofs. You can kind of see this if you've done much formalization yourself. You can see this especially if you see AI formalizations. They end up being much longer than the informal versions. But in each of these cases, the informal versions were human-sized. It was something you could read the proof and then translate it, or an AI could do the same. It's a reasonably sized thing. And like I say, mathlib's global coherence allowed me to apply probability, and looking for generality helped me find more interesting ways of applying topology in my context. Okay, so this is kind of a fairly standard formalization thing so far, but I think there's an aspect of this story which makes it quite a bit more interesting. So I mentioned this result proved in 2021, that if I have a set of integers of size 4, then it has a 3 coloring. I started reading this proof. Here are some quotes from the paper. It is possible, though tedious, to prove the entire theorem by hand. Okay, well, this is not great news if I'm looking to formalize something, because formalizing a proof is usually a bit more tedious than proving it by hand. So this is not a great sign. But I kept reading. Thus, in the interest of simplifying the exposition, we verified. That sounds good. I quite like this. Using a computer search, that for every S with diameter at most 288, there exists an S polychromatic 3 coloring. Okay, verified using a computer search. I'm back again to not really feeling comfortable with this. Maybe this seems tricky. But how many of these are there? How many sets of diameters at size at most 288 are there? 288 choose 3, so that's 4 million. So I have 4 million cases to verify, or some software to verify. This is usually bigger than most lean proofs. This is usually bigger than most mathlib proofs. You usually don't have more than about 10 cases. And it's important to know this is the only proof we know of, and this is the one I wanted to try and formalize. Okay, so now my work has gone from playing with topology and playing with colors to needing to verify 4 million cases. So I wanted to look into this computer search a bit more. I quote from the paper again. The code for the search has been included as an ancillary file with the preprint of this paper. So I tried running that file. It It didn't finish after an hour, didn't finish after 3 hours, didn't finish after 12 hours, didn't finish after a day. I get worried. I let it keep running. It didn't finish after 3 days. I happened to be friends with one of the co-authors of this paper, so I reached out to him. I said, you said it's tedious. Is it actually possible? Do you have one? Did you ever write it down? There's apparently a handwritten version in someone's notes without any computer search, but it was never shared. He has since retired, and these notes are in one of some non-trivial number of boxes. Okay, so this is not looking great if I want to believe this proof. Can we salvage it? I've got some code which I can't get to run. I have some proof which exists somewhere in some nebulous box. I have some people who, this was maybe 7, 8 years ago, and it's understandable that you'd forget a detailed proof like this after 8 years. So what can I do about this? I used more computation. So I poked into the C++ code. It turns out that for most of the 4 million, so from 4 million, you can do some reductions to get it down to about 900,000. And the C++ is only checking that 900,000. But amongst those, it's only actually slow for a very small number. It's only actually slow for about 1,000, 2,000 of them. And most of the others are really fast because it's C++ code. It's not heavily optimized, but it's not doing that much. So it's reasonably efficient in most, but not all cases. So for most of them, it finds the coloring we're looking for fairly fast. So I can just write that to file and save it, and now I have the thing in most cases. But what about the rest? So I asked a friend can you think of a more efficient algorithm to do this thing? And he said, yeah, maybe, but I know some software which will probably do this better. Because in each individual case, this is a combinatorial optimization problem. It's a finite search. And so I'm thinking about Lean. I'm thinking about software which can do combinatorial optimization problems. And so I think about Z3. So for the cases which don't finish fast enough in C++, I instead send them to Z3, which we heard about on Tuesday. It's a theorem proof from 2012, which is particularly good at software verification tasks, and in particular for me, solving combinatorial optimization problems. So for this roughly 1,000, which the C++ didn't work for, I instead send them to Z3. So I use Z3 to fill in the gaps, and now, I use Z3 with Python to get the search over the line and dump out the colorings you get in each case. So now, in combination with this C++ code, this Python code, this Z3 code, I should have a valid coloring for each of these essentially 4 million cases. Now, how do I put this all in Lean? I've got two options. I could either verify their code is correct and then run it in some verified way, or I could take the colorings which I've now generated, and instead of verifying the code which generated them, just verify the colorings themselves. Because each of these is just a coloring, and it's a periodic coloring, in fact, so it's now a finite check to make sure that each individual one works. So this is what I did. I read each one of these colorings into Lean, and had Lean check that for each particular set, this particular periodic coloring does do the job I need it to do. This is an example of certificate-based verification. I'm not verifying Z3, I'm not verifying C++ code. I'm just verifying that the output that those things gave me has the properties I need it to have. So this is not the typical framing of software verification, but in this case, it does exactly what I need for the software, which is that the output given in these particular cases that I care about has the properties I need. So I'm just verifying the output, not verifying the code itself. And this is not something you can always do, but in this case, that's quite a bit simpler. And so that's what I do. And this entire process of reading it into Lean and checking in Lean that this works, this is really convenient because Lean's metaprogramming setup is written in Lean itself. So I'm just writing more Lean code. And so this turns out to be a really nice process. And then to check each individual one works, because I've got 900,000 things to check now, I ended up writing kernel-optimized bitwise and bit masking operations, which check each individual one very efficiently. And so I end up with this statement. So this is the formalization of the previously computer part of the search, and this is verified in Lean now. So this is for every A, B, and C, where they are in increasing order, and C is at most 289, then there is a polychromatic coloring of the set 0, A, B, C. And so I have exploited some symmetries in the question. The property of having a polychromatic coloring is invariant under translation. So I can just translate so the smallest element is 0, and then do a couple of tricks like that to make this feasible. Okay, so that's mostly what I want to talk about. So let's summarize where we are. Lean enables a formalization of a huge range of mathematics. You can do traditional maths with topology and combinatorics and probability, or you can do kind of more modern style, large-scale search proofs as well. And mathlib enables us to do this increasingly quickly as it grows. And the fact that mathlib is one nice coherent library makes this really a pleasant process to do. And when I went into this, I went into the project thinking I have to verify 4 million cases. How on earth am I going to do this? But it turns out these things are not as bad as they might seem. And so I would encourage you to be in the mindset that when it comes to verifying in Lean, nothing is impossible. Might be hard, but it's not impossible. I need to acknowledge a lot of people who helped me with this project. That's a list of people. Each of them helped in some fundamental way to help me get this over the line. And one nice thing about this list is people who've worked on Lean in very different capacities. So yeah, thank you to all these people, many of whom are in the room, for helping me get this over the line. One last thing before I finish, I would like to show you my project website, which is here. It's on my GitHub/Polychromatic. And in particular, here's the code I mentioned earlier. But this is generated using Verso. And so what that means is I've said that A is in S. Let's say I want to know the type of A. If I hover over it, it tells me that A is in G. And so this is essentially Lean code embedded in the website, but in a Lean-aware way. And so I can also see proof states at different points in my argument. And this is all, we have hovers. And so, yeah, thanks for the Verso team for helping me make this and get this working. OK, that's everything I want to say. Thank you for your time.
Okay, so I think we have time for a couple of questions.
So thanks, Bhavik, for the excellent talk, as usual, spoiling us. Have you used any AI?
Most of the prose on this website was by AI. I wrote some documentation in my files and then asked it to improve the documentation and then use the documentation to make the website. So lots of this was with AI. One thing I didn't quite, so here's a nice graph describing the overall progress. So what I sketched for you is the proof of this one and the proof of this one. But the actual main result also needs the case of large diameter. So I verified the case for small diameter, which was the computer search, but not the case for large diameter. So that's work in progress. I sent that off to Aristotle last night to see what it would do. And last updated 12 seconds ago, 7 hours ago. And it's, completed. OK. I think it completed while I was talking. So I will check that afterwards. So yeah, we'll see.
Thanks.
Oh, actually, one thing to mention is that Z3 can be seen as a form of AI. It is kind of computer-assisted reasoning. It's kind of more old style rather than generative or new style things. So one could argue that, but I don't think that's the sense in which you meant the question. Yeah.
Thank you. So would it have been possible to verify all 4 million cases directly in Z3? Or do you have any idea of how much it would have taken?
This is a good question. I think it would certainly be possible, but I think there is some overhead in setting up the Z3 instance for each individual problem. So for many of the cases, you don't need to do that much search to get there. And so a more naive C++ search has lower overhead to get where you need. So the C++ is essentially a weaker algorithm, but with less overhead. So for the small cases, it's more efficient to use the C++ version. But for large cases, when the search is the constraining part and I can accept the overhead in setting up the instance, the Z3 version is better. So it would work, but I think overall it would be slower to do that.
Thank you.
Just 1 second.
How long did the Z3 computations take overall? Shorter than 3 days?
Great question. So let me give you some more timings to put these things in context. the C++ version, once I'd filtered out the ones which were slow, so like this is 900,000 minus about 1,000, went from taking over 3 days to 2 hours. And then the Z3 ones to fill in the gap took about an hour. And then for Lean to verify that these all worked, my original implementation took an hour, but then I optimized it with the help of some of the people in the Fro, and so that's now about 2 minutes. So the Lean verification of all of these 900,000 cases is now minutes, like 2 minutes.
Yeah, very nice talk. Thank you. So I didn't quite follow the significance of 288 or 289.
Yeah.
I mean, is it that if you can prove it for sets of diameter at MOSAT, it's true for the general case as well, or you don't know for larger than 289? Or
Yeah, so I didn't make this completely clear. The way the informal proof is structured is that for sets of which have diameter smaller than 289, you do a computer search, and for sets which are larger than that, you just have a regular combinatorics proof. So it is known in both cases, but the proof just kind of bifurcates into these two cases. And what I've done so far is the one which I thought would be the hard one, which is the computer search version, and what's left is just a bog standard combinatorics proof, which I haven't done yet, but should not be difficult in any way. And 289, just at some point in the proof, it turns out that some particular argument works if C is more than 17 squared, and 17 squared is 289, so it just drops out of the informal proof for the other case.
Is there any other question? Okay, so let's thank again Bhavik.
Thank you.